Yes.
Okay, are we waiting for more people to show up, or that's what we have at the moment? Okay, doesn't matter. The important guys are here. So it's a great pleasure to have with us today Shmuel Bialy. Shmuel did his PhD in Tel Aviv University back in 2018, right? That's right. Then
I
he
finished,
moved,
yeah.
finished, right? Then he moved to Harvard, spent 3 years as a postdoctoral prize fellow in the Institute for Theory and Computation. It's a great place. I know it in person. So, and then since last year, he moved to the University of Maryland, so a few hundreds of miles down the road, where he's now get another position in there. So, though it was short, I'm sorry for that, but please go ahead, Shmuel. It's all yours.
Okay, so thank you so much for the introduction and for having me here. And thank you all for coming. I'll start with sharing my screen. Do you see my screen?
Yeah, I can see your screen.
Okay, so from far away, but still here, thanks to Zoom, I want to talk to you about this topic of how do stars shape the interstellar gas around us, and specifically about these three avenues through the action of supernova, cosmic rays, and UV radiation. I know people here are interested in both supernova and cosmic rays from a different perspective. So we'll talk a little bit about the perspective from how they interact with the gas in the interstellar medium, ISM. And this work, it's basically summarizing some work I've been doing in the last few years at the ITC in Harvard with my collaborators here with Alyssa Goodman and others, as well as collaborators from worldwide, from Vienna and Max Planck and Florence, listed here. But before we go and dive into the interstellar medium, let's just take one step back and look at this nice image, this picture by Van Gogh. So this is the Starry Night, and this basically is what we see when we go out at night to look at the sky. We always look and we see the stars, and this looks a little bit sometimes like astronomical observations. No, not really, just kidding. But really in between the stars, there's much going on. And there's a lot of interesting physics that is happening. And this is, for example, the image of the Milky Way galaxy from Gaia. What we see here is, except from the stars, there's very apparent these dusty gas clouds all around the place, these gray striations. And these clouds, they can come in different sizes and temperatures and densities. And often when they become cold and dense, then the formation of new stars begins. Once the stars form, then they back react on the interstellar medium, and that would be the topic of this talk, how they interact with the interstellar medium. So basically, I'm talking about this cycle that the interstellar gas goes through. So let's imagine, for example, we start with the phase of atomic interstellar medium here to the left. What is happening is that the ISM is cooling through collisional excitation that releases then the atoms relax back to the ground state, releasing a photon, and therefore cooling. The photon escape into the intergalactic medium, and the gas cools. The gas cools, and then it can contract and become denser, and then we have the formation of molecular clouds that are dense and cold, typically of about a few hundred or even few tens of degrees Kelvin, and densities of up to 10 to the 6 or even more particles per cubic centimeter. These molecular clouds are the sites where new stars are forming. Gravity takes over and allows the collapse and the gravitational fragmentation of these molecular clouds to form even denser entities, and that's the stars. Once fusion begins, then you have a new star that formed inside. However, there is the other process, and that's what I will call in this talk feedback. Once the stars form, they start now injecting energy back into the system through different avenues. They insert energy through emission of UV radiation. They eject winds. And finally, if they're massive enough, they can also explode as supernova, which also then inject mechanical energy into the interstellar medium. These roots, basically, they shape, as we'll see, they shape the interstellar medium. They first of all, they affect the temperature, the density, the chemical state, and the ionization level, and therefore also the coupling and the two magnetic fields. In turn, this all regulates back the star formation process. And this is something I was talking about more the previous year, this regulation process on large scales. But today I'll really focus on how the supernova and the cosmic rays affect the cloud structure in these different aspects. I will not talk about large scale. I'll just mention it in passing just for a second here, and then I'll go back to small scales. So it's interesting to note that these feedback processes are also important, not just on cloud scales or within galaxies, but also globally on cosmological scales. So here, for example, we look at the evolution of the universe, the famous diagram, looking from left to right, from the epoch of the Big Bang, expansion of the universe where it was a soup, and then recombination, the time where the cosmic microwave background was emitted. Then we had the dark ages. That's the time where still the first stars and galaxies have not formed yet. And then the first galaxies have formed, and that's, by the way, very relevant for today, because hopefully in a week, or I think 22nd of December, should JWST be launched, and that's one of its primary missions, to look at the formation of the first galaxies and stars. Hopefully, fingers crossed, everything goes by plan. These first stars and first galaxies are now thought to be the ones that re-ionize the universe through the emission of UV radiation. Active galactic nuclei also play a role, but we think today that most of the role is played by UV radiation from dwarf galaxies. So on global scales as well, the radiation from stars also affect the universe as a whole. But as I promised, today I'll focus on smaller scales and specifically talk about, yes, Asaf.
Just to, I mean, I'm sure you're going to say it, I'm just cutting it down. So we know that stars do form even without this feedback, right? Because we had the first stars that were formed before this supernova.
Yes.
So how big is this effect? Is it like a small perturbation, or is it something which can change the result by orders of magnitude, let's say the rate of star formation? Or
right.
something?
No, it does change the result, but by quite a lot. And thanks for bringing this up. So first of all, in most cases, the feedback is negative, reducing the amount of star formation. So if you don't have feedback, you can still form stars easily. It's just that you form actually more. And if you have feedback, as you would naturally also naively expect, you inject energy into the system, it tends to heat things up rather than cool them, and therefore prevent star formation. And the effect, at least on global scales, is that the star formation rate that you'd expect if you did not have feedback would be about 100 times more the rate of star formation than what you get given that you have feedback. And this is, for example, observed from the famous star formation law, the Kennicotte-Schmidt relation, when you look at the star formation rate density as a function of the gas surface density in galaxies, and they see that you get an efficiency factor of about 1%.
So it's a one. So when you have this feedback, you can go down to only 1% of the rate in which you're forming stars without it. So it's a huge.
Yes, this is correct. Yeah, this is an average effect. Of course, then you go dive into details, what kind of galaxies, what epoch, and there's different details in that. But generally speaking, yeah, the feedback is very, very important, and this is one of the important takeout that people have realized within the last few years, where hydrodynamic simulations become much more sophisticated and allow the inclusion of these feedback mechanisms. And then people realize that how important feedback is. So now in this field of star formation and galaxy evolution, feedback is now, I would say, maybe the most important component that is very widely studied. And then, people look into what feedback processes at what epoch, what is important, what is less important. But it's very clear that this is the very important ingredient to be included. I study feedback from smaller scales to understand and then implement it in larger scale simulations. That's the main goal, and like looking, years forward. So today I'll talk about specifically, I'll focus about these two feedback avenues, which I've been working on recently and thinking of new ways to constrain them. And that's supernova feedback and cosmic rays. I've also worked on this on the third avenue of UV radiation, and I'll be happy to discuss this maybe after the talk. I'll say a few words about this in this talk, but won't focus on this. So let's start with supernova. So the effect of supernova on the interstellar medium has been recognized for years. And the seminal paper by Chris McKee and Jerry Oestreicher from the 70s highlighted how the supernova in our galaxy and in other galaxies tends to produce a three-phased medium. And the idea is that you have explosions of supernova and large supernova bubbles that explode from several supernovas that together drive shells outwards. Within these shells, you have a lot of heating in the gas, and the gas become hot of about 10 to the 6 degrees Kelvin and ionized. This is what's called the HIM, the hot ionized medium. And these shells expand and run into clouds that are neutral, composed of warm and cold neutral medium, the so-called WNM and CNM, which is the multi-phase neutral medium composed of mainly gas of a few thousand kelvins and about 100 kelvins. And we'll talk a little bit more about these two phases, WNM and CNM, in a second. But the general idea to take from here is that a large fraction of the volume in the interstellar medium is expected to be filled with these shells of hot and dilute material because of the supernova that are exploding everywhere as stars are forming and dying. And this highlights the negative aspect of supernova feedback, where the shells that expand and they run over these clouds of neutral gas that would otherwise form stars, but as they are run by these hot gas bubbles, they are evaporated through thermal conduction, and then they do not form stars anymore. And this kind of regulation process that does not allow the interstellar medium to collapse as a whole and to form stars very efficiently, because the supernova heating prevents many clouds from collapsing by heating them. This is a known picture that has been known for a while. However, here I'd like to focus on maybe less intuitive idea and maybe somewhat surprising. Well, actually, supernova can also, in a way, promote star formation and help the formation of molecular clouds and cold clouds to form, and then therefore, the story continues. Of course, the cold clouds, they collapse through gravity and form stars, as we said. How can this happen? How can supernova help the formation of cold gas and dense gas? So let's look for a second at this diagram that we see at the right. By the way, do you see it, or you don't see the faces that I see from this Zoom, right?
Oh, we see that. We see your screen.
Okay. No, because on my screen I see also a few faces. The Zoom. Okay. So what you see in this diagram is the thermal pressure as a function of the density in the neutral interstellar medium. So now we're focusing on the neutral phases, the neutral clouds, these warm and cold neutral medium that we saw in the previous slides, what are arranged into clouds. And the curve that you see is the equilibrium, is the steady state solution for the heating cooling equations. So basically, if you ask yourself, I'm somewhere in the interstellar medium, there are different cooling and heating mechanisms that are happening. And basically cooling is what we said, you have particles that are colliding, exciting energy levels, and then as the energy level relaxes to the ground state, it emits a photon, the photon escapes the galaxy and therefore takes the energy away and the gas cools. So that's collisional excitation followed by radiative decay. That's the main cooling mechanism. And heating is, in most cases, by the UV radiation from stars. So you have heating equals cooling. You ask at what temperature and at what density heating equals cooling, and you get this famous S-shaped curve. And what does it mean? The way to think about it is in the y-axis, you have the thermal pressure. So you can, the thermal pressure is often balanced by the hydrostatic, is often maintained by the hydrostatic pressure of the galaxy. So it's kind of a similar idea as you're sitting now outside, going outside, and you feel the pressure of the atmosphere on your head, and this produces some pressure in the air. So the same idea about the galaxy, it's like an atmosphere. You're sitting somewhere outside in the galaxy, you have a pressure that is maintained by the gravity of that a gas layer. And then assuming you have some pressure, let's say it's 10 to the 5 or 10 to the 3 in these units, you'd get a density and temperature that is determined by the cooling and heating processes. And what you can see is that if the pressure is about 10 to the 3, and that's about the pressure that we have in the interstellar medium of our galaxy, the solution is a warm and diffuse gas of about 10 to the 4 Kelvin. Now, if you want to form stars, you need to go to much higher densities. So you need to go to the upper right of this diagram at about 10 to the 3 particles per cc and much higher pressure. So you want to jump above this strip from warm diffuse gas to the cold neutral medium. And by the way, this the region of pressure where there's two solutions, you see about a few 10 to the 3. This is called the multi-phase interstellar medium, and the branch in between is a thermally unstable phase. So this is an interesting topic by its own, but I won't go into too much details of this phase diagram now. It's called the phase diagram of the interstellar medium. But the basic idea is that, let's say you're somewhere in the interstellar medium, you're warm and diffuse at 10 to the 4 Kelvin, and you want to form stars, you need to get a compression to jump above the thermal instability and to cool down to lower temperatures and higher densities. And to get this compression, you need some sort of perturbation, of a density perturbation or pressure perturbation. And the question, how you get that? So there are different ways to get this pressure perturbation. And the one of the ways that is very attractive is through shocks that happen in expanding supernova shells. And the idea is that we have these expanding shells we saw in the first image. These expanding shells, for a long time, they are supersonic, which means that you drive a shock. And once you have a shock, you go basically along this line, you go, let's say you start from here, you go up to higher densities and higher temperatures, also higher thermal pressures. This is the gas in the shocked layer at the expanding supernova remnant. Now, if the supernova remnant continue to expand, then after long enough time, you start to cool down, because if you're on this curve, it means cooling equals heating. But if you're not on this curve, then cooling and heating are not balanced. Above this curve, cooling exceeds heating, cooling is more efficient, and below this curve, heating is more efficient. So basically, if you go out of this curve because you're shocked, now you're at higher temperatures and higher densities, cooling becomes more efficient, and now you start to cool efficiently until you reach the phase of the cold phase and dense phase. So basically, the idea is that even though the expanding shells, they hit the gas, but they can also take it out of this thermally stable phase and allow cooling mechanisms to kick in and become more efficient, and eventually you end up with a cold and dense shell at the edges of the supernova remnant. And this has been shown in a series of papers by both analytically and in simulations. Yes, Asaf.
I have several questions about what this plot basically. So I have three questions actually. So my first question is, you are describing, I mean, this line basically describes some sort of an equilibrium state, right, between cooling and heating.
Yes.
What is the characteristic time scale for reaching this equilibrium?
Yes, a great question. So it depends where you are at. So to reach the equilibrium state at the warm phase, this time scale is quite long. It's about 1 mega year or a few mega years, depends on metallicity.
Mm-hmm.
And to reach the cold state, actually the time scale is much shorter. So here it can be a few thousands of years and up to 10 to the 4 years.
So if it is so long to get the warm state, right? During this time, you have a lot of stars that explode as supernovas, etc. So why is it reasonable to assume even that you have an equilibrium state?
That is right. On general, the interstellar medium is it always goes through these phases, and sometimes it does not reach equilibrium, but tends to reach towards equilibrium. And the better description is through simulations which take into account the cooling and heating processes. These simulations, hydrodynamic simulations that I mentioned before, and they have all these heating and cooling components, they show that gas indeed goes along these lines, but there's also out of equilibrium gas because of exactly what you mentioned, that the time scale is long. However, it's marginally long. It's not much longer than other typical dynamical scales, specifically, for example, turbulent turnover time that happen in the interstellar medium. So if it was very, very long, it would be meaningless to even look at this diagram, I agree. But this is comparable to other important time scales in the problem. So the gas tends towards this phase, but not always reaches it.
Okay, then my second question, you mentioned that the pressure, you say it's due to the effect of the other stars in the galaxy. So is it just a gravitational pressure?
It is a combination. Yeah, it's a gravitational pressure, which is a combination of the self-gravity of the gaseous disk that gravitate itself, and as well as gravity by stars and the dark matter potential.
So dark matter is included when you calculate this.
Dark matter is, yeah, it's also important and included, yes.
And my last question about this this yellow arrow that you show, and what happens when you have heating by supernova shocks. How do you increase the density without while keeping the pressure constant? Well, what is the physical mechanism?
Okay. So the idea here and here as well, it's important to, this is this is a cartoon. In fact, the real track is not a straight line. It goes like this, and then at some point it starts going down. And again, the details depends on exactly where you are and what kind of shock you have. But the idea here is that for some period of time, you're inside this shock, and there is something that is pushing outwards and creating in the shock a pressure that is elevated. In reality, the pressure does change. It's not constant, but the important point that it is above this critical pressure shown here by this point. It is above this point, and therefore you're allowed to cool. So yeah, it's not a straight line like this. It does go up, and then at some point start going down.
But then don't you talk only about some shell behind the shock wave?
You start to cool, and then the shell increases in size and also by mass as time goes by. So there's condensation of gas onto the shell, and more cooling, and the shell increases in size as it sweeps more and more gas from the interstellar medium.
Okay.
So most of the mass is not ejecta or anything that was a part of the supernova. It's the interstellar medium that is swept up by the shock wave.
Okay.
And yeah, the important point here is that for this to be possible, you need the dynamical time of the supernova remnant to be comparable or longer than the cooling time, which we said about a mega year or so. So this mechanism really becomes effective at older ages, not in your classical supernova remnant that are young and shiny in X-rays. At this point, this mechanism is not effective, and the effect is mainly negative feedback. This mechanism becomes effective at about an age of a mega year or so, where cooling can kick in.
Okay.
And here is an example from a simulation, a hydro simulation run by a group from Max Planck in Germany. It's a famous suite of simulations, the Silk simulations, that basically what we see is a section looking up from top to bottom on a galaxy. This is the left, and looking edge on a galaxy, on a section of the galaxy. We're looking at the density slice. These simulations include cooling and heating, chemistry, basically formation of molecular hydrogen and CO, supernova, stars, and gravity. And this just to show the effect, just to get an impression of what is happening. So here you have the explosion of supernova that drive these shells that we are talking about. And what you see here in gray, this is denser gas that is in this phase of the cold and the dense neutral medium at higher densities that is often found at the edges of these supernova bubbles and super bubbles that are expanding outwards. And in this group, there are different simulations. They explore different feedback processes. So there's a lot of details. I just wanted to show this as a means of illustration of how this looks like. Okay, now from the point of view of observations, this effect of positive supernova feedback and the formation of clouds and condensation of clouds, this has been shown, this has been investigated and shown more in a statistical way, looking at galaxies and the number of stars forming in and out of shells, but never has been this observed directly in a galaxy, in our galaxy or in other galaxies. And the reason is exactly what we said, is that this cooling only becomes effective at old ages, where the supernova remnant is no longer visible and easy to find as it is old. And also the other effect is that we look at the interstellar medium, we always look in 2 dimensions. We always see everything along the line of sight. So different structures are blended together, and it's very difficult to understand what is the real structure of the interstellar medium because of this 2-dimensional view we have. And this is, for example, what we have here. What I show is the Planck map of our galaxy. This is the midplane. And here I highlight in blue and red 2 famous molecular clouds that are star forming today in our solar vicinity, the Taurus and Perseus molecular cloud. And for example, as you see here, they seem to be touching each other. And the problem is, because of these 2 dimensions, it's hard to say what is happening. So for example, in this image, you see this person is very large, but we know, of course, that they are the same size. And the reason that it looks like this is because this picture was taken in the Salar desert in Bolivia. Maybe some of you were there. And there the floor is special, the ground. So it's hard to locate where the person is standing. Is he standing close by or far away? And therefore it's hard for us to understand what's its real size. And this is exactly the problem in the interstellar medium. We don't have access to the distance dimension, distance along line of sight. And therefore we don't know if Taurus and Perseus are really touching each other, or maybe one of them is at the front and the other one is at the back. And also, generally speaking, just how to say what is the real structure and the sizes of clouds and the real structure of the gas in our galaxy. Now, recently, there was a big advance in this field, and that's the release of the construction of three-dimensional dust maps. And this direction of 3D dust map has been there for a while, but really recently there was a big leap forward because of Gaia. And what's the idea? How do you produce a three-dimensional map of the gas? Is basically from the extinction of starlight by dust, you know the column density from you to the star. So basically you look at different stars, you see how the light is extincted by dust, and you know how much dust is between you and the star. So you see this, you get this sigma. So basically the integral of the volume density or mass density along the line of sight, so rho dl. And you can do this for different stars. So you see one star, the next star after it, and from this you get the how much mass of dust or column of dust there is between you and different stars and the next star and so on. However, now with Gaia, you could recently also get very accurate distances to these stars. So now you have the mass between two stars, the mass of dust, and now you also know the distance between these stars. So you know this dl, and basically you can disentangle these two and get the 3D volume density, rho or n, doesn't matter, it's just divided by the mass. So you can get now in 3 dimensions, what is the density in each point in the 3D volume of dust. And recently there was a very accurate dust map by Like et al. With 1 parsec resolution mapping the entire interstellar volume around us, showing up, basically revealing new structures. And this this is something we studied recently, and we focused on these 2 clouds that you saw, Perseus and Taurus. So as an example here, you see again Taurus in blue and Perseus in red. This is as they seen from the 3D dust map. So I just isolated these 2 clouds, and now I can rotate around because we have the 3rd dimension. First of all, we see that these 2 clouds are actually not touching each other at all. They're at very different distances. Taurus is at 150 parsecs, and Perseus is at 300 parsecs. And now these blue and red show you the density at a isosurface level of about 30 particles per cc. We can also look at lower density gas. So here showing in white, now we are looking in white at the gas at 5 particles per cc. This view that we are looking at is how it shows up as you see it along the line of sight from us to these clouds. So as you see, if you look at this like this, you don't see really nothing. All the structure is blended together. But now you can rotate it. And now when you rotate, you see that actually there is a cavity, there is a void in between these 2 clouds, a region of lower density material, and the gas that's surrounding these clouds actually curves up to form something that resembles a shell. Now let's look deeper into this and see if it's really a shell or maybe just our imagination. So looking deeper into this structure, by the way, this structure has not been identified before, and we discovered it for the first time just a year ago. And this is really thanks to this new data set presented by this amazing 3D dust map with a very high resolution. Before it was not possible because we just didn't have such a high resolution and accurate dust map. So here again, we see these isosurfaces of 5 particles per cc in gray, and the blue shows the higher density surfaces. Here is the sun. Here the sun again from different angles. This is the Taurus cloud and its envelope. This is the Perseus cloud and its envelope. And this is the model that we built for the shell. Of course, in reality, the shell is not a perfect sphere. It's just for simplicity, we show here a sphere. These are 3 density cuts through the different planes, XY, XZ, and YZ. And you see here the density enhancement at around a radius of 80 parsecs. So the radius here is 80 parsecs. This is the shell radius. These are different radial density profiles. This is the mean density. So here by mean, I mean at each radius, you go to that radius and calculate, there's different density at a given radius, but you calculate and show just the mean. So for example, here all these densities, but you just show the mean. And these are different density percentiles at each radius. So here is the center of the shell, the point. And here as you go out is the increase of the density of the mean density and the increase of different density percentiles. And then the decrease as you go out to radii larger than 80 parsecs. In the two other panels, you see the volume, the fraction, the volume, the volume fraction filled by different densities and mass fraction. Yeah, I saw stuff you raised your hand. I'll answer you in a second. So basically what you see here from these big spreads is that at any radius you are, there is non-uniform density. The ISM is very inhomogeneous. You always have lots of density fluctuations. So for example, you can, at a given radius, if you are at the shell radius at 80 parsecs, you can find gas of more than 30 particles per cc. You can find a gas of 1 particle per cc, 3 particles per cc. But generally speaking, the probability to find higher density gas increases by significant fraction as you go to a radius of 80 parsecs. Whereas if you go towards the center, the probability of finding dense gas is very low, and mostly you'll find very low density gas. Yes, Asaf.
So this model that you're promoting is very interesting. So it basically states that there must have been some explosion at the center. So my question is, was there any search for any remnants, like a pulsar or any leftover from the star that might have exploded?
Right.
Center between these two clouds.
Yeah. So I did search for a pulsar in the center. There, I did not find it in the catalog of pulsar. I did not find a pulsar there. I was not lucky enough. By the way, Hagai from the Technion asked me an interesting question, which I should look at, is what are the chances given the volume? What are the chances that we don't see a pulsar? Because given an angle of the pulsar, you can estimate how likely you are to find a pulsar or not. So this I don't have an answer yet, but we did not find the pulsar. Another interesting question, which I want to look into, is maybe the finding neutron star from the cooling radiation. This might be also very difficult, but maybe it's possible. This is at about 200 parsecs away from us, so I don't know if it's possible to look and find the neutron star from that avenue. Do you think it's possible, or is it too far?
Not an expert in the pulsars. But,
yeah.
I think as far as I know, you have seen pulsars in the more distant regions, so I'm not sure it's impossible.
Yes, no, the pulsars is easy. I mean, it's if the pulsar, the thing is you have the pulse and it's very bright. So if you were lucky and the pulse is in your direction, you will definitely see it towards very high distances. The problem is that often you're not lucky, and even there is a neutron stars with the pulsar, but it's not directed towards you. But the neutron star is still there, and then the neutron stars is cooling and emitting thermal radiation, which is much harder to see, but it happens to all neutron stars, unlike the pulsars, which are only if their orientation is right.
I wanted to ask a question. There is clearly a preferential direction here. And do you expect that the pulsar will be in the same direction, or do you expect, is there a link between the direction of the pulsar and the direction towards which you see the concentration of the clouds?
I would say it might have to do with the location of the pulsar, not the direction. I don't think it will have to do with the direction the pulsar is rotating, but more towards the direction the pulsar is, because you might have a general, let's say you had a stellar cluster in the center where the supernova went off, and there was some general velocity of that cluster in respect to the interstellar medium around it, then the remnant, the pulsar or the neutron star will also move with that direction. There will be an offset between the velocity of the stars and the shell, because the shell is slowing down with the interaction with the interstellar medium. So this might have to do with that the remnants won't be exactly at the center, but would be offset. What we did find some evidence for potential evidence for a supernova is not from the compact object, but rather from the gas. So what we look here is the recent release of the recent image of the eROSITA map of X-rays. It's not a release because it's not publicly available, but we did took the image from the internet, and we were able to hack it and to actually draw the contour of the per tau shell. Basically, it's looking at how this shell would be projected on the two-dimensional sky of the eROSITA image, and this is what you see by the green outline. This is the outline of this shell. By the way, we call this structure the per tau shell, per for Perseus, tau for Taurus. So this is the outline of the per tau shell on the sky. And here we identified a previously unidentified source of X-rays, of a soft X-ray diffuse emission towards the center. This is this green blob. We're waiting for the data to be out, and then we could make more analysis. But for now, I just say that there is this emission of X-rays might suggest that there is hot gas produced by this supernova explosion at the center of the per tau shell. We can estimate also the age of the shell and the number of supernova remnant, the number of supernova required. We have the two clouds, the Perseus and Taurus, at the front and the back, which are detected in CO. So we have a spectrum, we have velocities. So we have velocity and we have radius. We can estimate a time scale, and we estimate a time scale of about 10 mega years. That's for the age of the per tau shell. Now you also have velocity and radius, so you can also estimate how much momentum should you inject into the interstellar medium to be able to produce this shell, comparing with simulations of supernova explosions and expansion of these bubbles, as well as analytic theory. And what we get is you need about 2 to 8 supernova, so more than one supernova to produce this large shell at 80 parsec radius. You can also take this back and ask, okay, if this is the number of supernova and I have a standard initial mass function, IMF, what should be the mass of the star cluster that was there at the time of explosion? And we get a reasonable mass of about 1,000 solar masses. By the way, these numbers are also consistent with some timescales and numbers that you can get. So for example, the age of the shell that is about 10 mega years is longer than the cooling time, and that makes sense. Otherwise, we would be in a problem. And also it is longer than the observed stellar ages of stars and Perseus and Taurus, suggesting that these stars could have formed after the compression and the formation of the cloud because of the per tau shell. The number of supernovae is also consistent with what you'd expect from core collapse supernova rate in our solar neighborhood. So I took here this value of 30 per kiloparsec square per mega year from a paper by Paravano et al. The area of the shell and the time, and you get about 3 to 13 in quite a good agreement with our estimate. So basically the picture we have is that, as we saw in the movie, that some 10 mega years ago, you had a cluster of stars in this region. Then this cluster includes mostly non-massive stars like our sun and below, but also has some massive stars. The massive stars, after they die, they explode as supernova. And it's typically found that massive stars are coming in clusters. They don't come separately. So if you have one, you probably have more than one. So one explodes, then another one explodes, another one. You have several explosions. These explosions drive a shell outwards. And this is the shell we see today. Now this shell is cooling down and allowing the formation of cold gas, which eventually turns into these two famous clouds, the Perseus and Taurus molecular clouds, which we know are forming stars today. So basically it's a sequence that you have a star formation supernova, the supernova form new clouds, which now form new stars. This is the picture. And to summarize, I would say that this story, the story of the Pertau shell, is a story of two things. One is how supernova may be not only destructive, but also help formation of stars, so basically positive supernova feedback. It's the first observational evidence of this process. And the second is that more generally, the move of the astro community in the of the study of the ISM and star formation from 2D to 3D really reveals new structures and changes our view of the interstellar medium and star formation. I'll just show you the large map. So what we saw was just a chunk of the whole 3D map. Here, this movie shows you the entire 3D map of our local environment. There's a lot to be done. So we just studied one region and found a surprising result, but really I would like to study how this gas is structured through various statistical methods. For example, is it really full with these shells, or was the Pertau shell an exceptional phenomenon? Connection with spectroscopic observations like CO and H1 would really be amazing, because now we have 3D position, and all the spectroscopic observation give you a velocity. So if you can connect structures from the seen in this dust map with structures seen in the molecular gas or atomic gas in COH1, you'd really get also the kinematics as well as the positions, and that would really be very helpful to understand the evolution of the interstellar medium. And finally, the connection with stellar data from Gaia, so with 6D positions, basically 3D position, 3D velocities from Gaia. So the connection with stars would give us a complete picture of how these things are happening. So for example, you can imagine if you take the stars in this region of the Pertau shell, and this is something we're doing now, and take the velocities from Gaia and backtrack where the stars have been 10 mega years ago, and then you might find, might reproduce the stellar cluster that gave rise to this Pertau shell. This would be the smoking gun. So this is all to be done. Yes, Asaf.
So really related to that, so my first question about this Perseus-Taurus system that you studied, are there any measurements of the velocities of these clouds via Gaia? And then or any other method? And the second is, are there any estimates on the physical properties, such as the total energy that was injected by the supernova? How strong must it have been to produce the observed structure that we currently see?
Yes. So for the first question, this connects really to this point that I made here. We have measurements towards. So you see the shell itself, it's very difficult to observe it as a whole, because as I said, that's why it was not detected before, because of blending along line of sight. So that's H1, which should trace atomic hydrogen, which should trace the entire shell. You see it, but it's hard to connect the structure you see in H1 to the shell. However, for the two clouds, which are denser regions in the shell, the Perseus and Taurus, and they lie at the front and back of the shell, this is something that you see also in CO, and from the Doppler shift of CO, you get the velocities. So you do have velocities of the two clouds, the Perseus and Taurus, and based on these velocities, that's how we were able to make estimates of the age of the shell based on the velocities.
Okay, and so, what about the energy?
And about the energy, this is basically this point I made here. So if you calculate how much energy should you inject to produce the shell and compare it with the typical energy of a supernova remnant, you get of a supernova, you get that 1 is not enough, and probably you would need about 2 to 8 supernova to produce this shell.
Okay.
Okay, so I want to say also a few words about cosmic rays before I finish. So here I just summarize that really in the field of the ISM, this is really, I feel this is very exciting, and it opens our eyes to start seeing structures in 3 dimensions and things you're just, guessing how things are structured. Suddenly we can actually look at them and investigate. And this dust map is a gold mine that we're going to study for several years more to understand how the ISM is structured. Now, supernova and cosmic rays are not two unrelated things. We know that cosmic rays.
I'm just giving you a warning that you've got about a little more minutes than that.
Okay, so I'll just mention this quickly about the cosmic rays, and we can always talk more if you're interested. So cosmic rays, basically they are accelerated in the sites where you have shocks, and this a main candidate to accelerate supernova, to accelerate cosmic rays is supernova, at least if they're not too much energetic, and the stuff you yourself were thinking about how you accelerate high energy cosmic rays and maybe gamma ray bursts. But now I'll be talking about lower energy cosmic rays, and in fact even lower than usually what people are talking about, because lower energy cosmic rays in the region of GeV to TeV are the ones that actually important for the study of the interstellar medium. So if you want to ask, before you form stars, you have these molecular clouds, these dense and cold regions of 10 kelvins or so degrees. What dominates the chemistry and thermal state of these clouds? And the answer is, it's the low energy cosmic rays. The low energy cosmic rays, they can penetrate deep into these cloud interiors where UV is not present, UV radiation. And they they basically catalyze the chemical reactions, forming different molecules, as well as even up to prebiotic molecules. They produce ionization and therefore heating of the gas, determining the temperature of these clouds, and therefore how would they form stars. And even coupling to the magnetic fields of the galaxy, because they produce ionization and therefore connect the clouds to the larger scales. However, to date, we have very bad knowledge of these lower energy cosmic rays. At high energy, there are different observations, for example, the AMS on the space station, Voyager, and other probes that can tell us what's the flux of these cosmic rays. Here is the flux as a function of energy. However, at low energies, here you see these are different models that are trying to guess what is the flux of low energy cosmic rays. And the reason is, even though we have Voyager observations, Voyager is still close to the solar system, and even if it went out of the heliosphere and is not affected by the bow shock, which is a question, we are still in the so-called hot local bubble. In any case, we are specifically located in a specific location. We don't know what is the flux and energy of low energy cosmic rays, and what is the ionization rate, and all the processes that we mentioned. Now, recently I had an idea of how can we use these molecular clouds to constrain low energy cosmic rays. So until now, these low energy cosmic rays were mainly constrained by very indirect observations. So people were using telescopes to observe different special molecules like H3+ and HCN. And via the spectroscopy of these molecules, they were deducing the abundances of these molecules, connecting with chemical models that involves a lot of knobs and uncertain variables to determine the so-called ionization rate of low energy cosmic rays. And therefore, there was a lot of uncertainty, and that's all the points you see here, in the true value of the cosmic ray ionization rate. Basically, because it involves these chemical models and these very esoteric molecules as a probe. Now, my idea was that we can actually use molecular hydrogen to directly probe the cosmic ray these low energy cosmic rays in the interstellar medium. And the idea is that you have these clouds are mainly composed of molecular hydrogen. So you don't need any of the chemical models or any conversion from so basically you're looking at the bulk of the cloud. Now, these molecules, the H2 molecules are sitting there. They are hit by a cosmic ray. The cosmic rays produce ionization, as we said. The heating processes is from these cosmic rays. They produce ionization, but what they also do, they also produce excitations. And these excitations is something you can see. So basically, the cosmic ray hit the molecule, excites vibrational and rotational and vibrational levels of the H2 molecule. And here is an example of the energy diagram of the molecular hydrogen molecule. So this is the distance from between the nuclei, and this is the energy level, and you see here different vibrational and rotational levels. Specifically, cosmic rays excite the first vibrational level of molecular hydrogen, so the molecule starts to rotate, to vibrate, sorry, and then as it de-excites back to the ground state, it emits an infrared photon, which we can observe. And basically, the idea is that the flux of the observed infrared photon is directly proportional to the excitation rate, which gives you the flux of cosmic rays in the cloud. Yes, Asaf.
How do you disentangle the excitations done by cosmic rays and excitation done by other means? Photons.
Yes, excellent question. So actually, it is such a good question that I wrote a paper just about this in 2020. So this is a plot from my paper where I looked exactly about this, comparing the cosmic ray excitation, the UV excitation, and the chemical excitation from the formation process of molecular hydrogen. So first of all, of course, depending on the ratio of UV to cosmic rays, you have different intensities. But the stronger way, I would say, is the line ratios. Because physically the process is different. In cosmic rays, you interact with electrons. So it's a particle with mass, whereas with UV, it's a photon. So the quantum rules are different. With a photon, you first excite the electronic state of molecular hydrogen, which cascades down. And with the electron, you directly excite the vibrational state. So basically, you get different line ratios for the two excitation mechanisms, and by that, you can disentangle the two processes. So these are the 4 lines that are preferentially excited by cosmic rays as opposed to the other mechanisms. These are the first V equals 1 and J0 and 2 levels of molecular hydrogen emitting at 2 microns. And I would just say, I don't want to take more of the time, I just say that following this new idea of observing cosmic rays, or I call it using cold clouds as cosmic ray detectors, because I'm thinking of it as like the Kamiokande floating up in space. Like you have here Kamiokande, super Kamiokande to observe neutrinos through their interaction with the liquid, the xenon or whatever there is in the, sorry, the super Kamiokande, it's not xenon, xenon is a dark matter detector. Never mind. So you have interaction of neutrinos with the liquid, producing emission that is then translated into neutrino flux. The same idea, you have these clouds, which are huge reservoirs of molecular hydrogen that are used to detect cosmic rays in space. And following this idea, I recently got time on the MMT telescope in Arizona, 6 nights to observe 6 clouds. We took their spectra, and unfortunately, we did not detect a line, because we now realize that from the ground, this is not possible to do, because there is too much noise, atmospheric noise, to do this from the ground. However, we placed limits. We placed limits on the spectrum and the cosmic ray ionization rates in this cloud. But really, the next thing, and I think this method is really suited and would be best done with this. This is, of course, this is the JWST, and JWST will be observing exactly at this wavelength length. And I've went forward with the JWST time calculator, And the prediction is that it would be very easy and we might get very high signal to noise ratio for the spectrum of this molecular hydrogen excited by cosmic rays, and from line ratio we could tell how much is excited by cosmic rays versus the other mechanisms. And we will be able to constrain then the spectrum of the low energy cosmic rays, and basically understanding the role of these low energy cosmic rays for the chemistry, heating, and magnetic fields in molecular clouds, the star forming regions in the interstellar medium. So I'll just summarize with this slide saying that we've seen that supernova feedback could be negative and positive. We've seen a first evidence for the positive effect of supernova feedback, and the future is bright in terms of the understanding the structure of the interstellar medium in 3 dimensions and the role of supernova in shaping it. We've also talked a little bit about cosmic rays and how can they be constrained in the regime that is currently very uncertain with upcoming JWST, potentially understanding better the sources of these cosmic rays and their propagation in the galaxy. Thank you.
Thank you, Shmuel. Any more questions from the audience, preferably from students first? I don't see any questions in the chat. Anyone on connected wants to ask a question?
Ofek, I can show some very quick movie if there is no question at this point. Can I?
Yeah.
Yes,
okay.
Go for it.
Okay, so what I wanted to say that, okay, we talked a lot about science, but actually this going from 2 dimension to 3 dimension also imposes a challenge in terms of visualization, like how to look at data in a different way, because looking at the paper, at the printed paper and the plot is not so useful when you have 3D data and you want to be able to play with it and see it. So in this paper, first of all, I encourage you to visit the website. There's a lot of, it got a lot of press release. So there is a lot of movies and also in 3D figure that you can play with. And in the paper, we have this 3D figure. But I also want to show, this was the first paper that was published that includes augmented reality. And basically the idea is that, let's say you have the paper, you have the printed version on your table. This is a figure from the paper. And you have a QR code in the paper that you can scan with your phone. And then with this QR code, you have an application on your phone that is augmented reality. Basically, you scan your tabletop, and then you can basically you see like the model and the data as if they are lying on top of your table or the paper. And you can walk around it and see the structures yourself as if it's a real structure in front of you. And here is a movie I took in a cafe in Cambridge. So that's how it looks from my phone. So this is the table of the cafe. It can become you can turn the opacity off or on. And I'm just walking around the structure, looking at the different clouds and just, exploring them as if they're real things from different angles. So I invite you. I can put the link in the chat and you can just play with it. And there is even something called a merge cube. It's like an actual cube that you can buy on Amazon for $10. And it's a special cube that has different QR codes all around it. And then you can also hold this in your hand rather than putting it on the table and like move it around, and you see as if you're moving the Peritau shell. And and this is another movie that we got from this.
10 million years ago, a supernova went off, creating an explosion.
This is from the
that
press
pushed
release.
gas and dust around it outwards. Remnants of this explosion exist to this day in the shape of molecular clouds, dense regions of gas where stars form. New research to measure the shapes and sizes of molecular clouds allowed astronomers to detect the empty cavity in space created by the supernova. The discovery shows that the Perseus and Taurus molecular clouds in red and blue and other molecular clouds form from the powerful effect
of supernova explosion. I don't know why it stopped. Anyways, so yeah, so there are some cool things going on in data visualization as well as a result of these new data sets. Yeah.
Very cool.
Yeah, and I posted in chat the website, so if you like, you can play around with the augmented reality or the videos or whatever.
Thank you.
Thank you. Thank you, Shmuel, again. If anyone else wants to hang around and speak to Shmuel, you're welcome to do so. I'm shutting off the recording.
Okay, אני נשאר פה לדבר. Hang off the recording.